Okay, so the final talk of the morning will be by Anna Miriam Benini, and she will speak on bifurcations in spaces of meromorphic maps.
So thank you for the invitation. It is such a pleasure to be here. I've heard about this place since I was in my PhD, and since my PhD, I have met Carsten, and though I never wrote paper with him, we had many mathematical discussions which were deeply inspiring for me. So I'm very thankful for all the mathematics that he shared generously throughout the years. And today I will talk about bifurcations in spaces of meromorphic maps. It's the first time that we have meromorphic maps appearing in this conference, and this is joint work with Mathieu Astorg and Nuria Fageia. So a meromorphic map, I know we all know this, it's a holomorphic map from the complex plane to the Riemann sphere, or if you want to see it otherwise, it's a map from the complex plane, it's a map for the convex plane to the complex in which has poles. So what is the special feature with respect to rational dynamics is that infinity is an essential singularity, and with respect to the iteration of the entire map is that it has poles. And I would like us to think today as poles as a way to move from the finite part of the plane to a neighborhood of infinity. Some orbits are truncated. Why? Because the domain is strictly smaller than the range. So if you have an orbit which hits infinity, there is no way we can iterate further. However, this is not going to be a problem. We will see that when some special orbits are truncated, we have dynamical phenomena. And I would like to point out that infinity really has a double role. So if we look at it in the domain, it is an essential singularity. It's a special point. But if we look at it in the range, it is just a value like any other. So it can be singular, or it can be a regular value. And holomorphic maps, in general, are coverings outside the set of singular values. And I will see a little bit more about this. And what we will do, we will look at bifurcation in holomorphic families of meromorphic maps with finitely many singular values. So finitely many critical points or asymptotic values. And we will define so-called natural families, which are the natural setting for us to study these types of bifurcations. I know most of you are familiar with this, but let me remind you what are singular values and regular values. So a regular value or a regular point is a point near which I can take a neighborhood, and all preimages of this neighborhood are going to be univalent. So if you want to think about it, all inverse branches of inverse are well-defined. A critical value is just the image of a critical point, and we all know that it means that it may have, if you take a neighborhood of a critical value, you may have some preimages which are univalent, but you definitely have one preimage, which is the one containing the critical point, which is mapped D to 1 for some degree D. And the new feature that you have in transcendental dynamics are asymptotic values, which are, well, the definition of asymptotic values we all know. These are values for which there is a curve tending to infinity, and the image of these curves tends to our finite value, or infinite value, because infinity could also be an asymptotic value. In practice, it's like 0 for the exponential map. And the feature of asymptotic values is that if I take a neighborhood of my asymptotic value, there is always one preimage, at least one preimage of this neighborhood, which is unbounded. And so what I would like us to think of today, well, the map is a covering outside this set of singular values. If you remove the preimages of the singular values in the range and the singular values in the domain, you get an unbranched covering. Okay, but what I would really like, the reason why I've shown you this slide today, is because I would like us to think as asymptotic values as a way to come back from infinity to a finite part of the plane. So poles allow us to go to infinity, and to go back from infinity to a finite part of the plane, we can use asymptotic values. Of course, it's not a neighborhood of infinity which maps to a neighborhood of our asymptotic value, because infinity is an essential singularity. But there are these open sets which are mapped back to a neighborhood of our asymptotic value. They're called tracts, just by the way. Okay, so what is a natural family? A natural family is a family of meromorphic maps. We will always assume finitely many singular values, otherwise you will see that nothing works. Anyway, it's a family of meromorphic maps defined over a complex manifold, and we want all our functions in the family to be deformations of some base point f. What is the precise definition? The precise definition is we want our family is to be parameterized by our holomorphic parameter lambda, and f lambda is our base parameter f, pre and post composed, with two quasi-conformal homeomorphisms. If you don't know what a homomorphism is, what a quasi-conformal map is, don't worry. The only thing you need to care about is that they are homeomorphism and that they have decent geometric properties that allow you to do the computations. And in fact, well, and the very important thing is that essentially this definition only implies that maps in a natural family have the same covering properties. Why is that? Think back about this slide and pick, for example, a critical value, okay? If you take, I'm going to draw this because it's going to be more clear. If I have a critical value for my map F, and I take, for example, the critical preimage, which contains a critical point, and this is mapped D to 1, what happens if I put a homeomorphism here and a homeomorphism here? The composition, which corresponds to f lambda, will have exactly the same degree d to 1 that f had. Same thing if you take a regular value, same thing if you take an asymptotic value, because if the preimage of this set was unbounded, I'm going to say something. So you want the change of coordinates to preserve infinity as an essential singularity. So you want, essentially it's like applying two different changes of coordinates, one in the range, which is C, and one in the domain, which is C hat, okay? So this is not going to preserve any dynamical properties because it's not a conjugacy, but it's going to preserve all of these covering properties because this is what happens when you have critical values and what happens when you have asymptotic values, that if under F the preimage is some unbounded set, when I apply a quasi-conformal homeomorphism of the plane, I will also get some unbounded set. And then I will have, again, our change of coordinate in the domain. And the composed map with these two changes of coordinates will have the same covering properties as F. So what is this? So really, in order to be able to prove this kind of theorems about studying bifurcations, it's important to start with a family which has the same covering properties. And another important properties of defining a natural family is that singular values move holomorphically. What do we mean by this? Take our family of maps parameterized by M, and choose your map, F, or if you want to be more precise, a parameter lambda naught. It will have a certain number of singular values, finitely many, for example, 3 in this picture. What this condition ensures you is that all of the critical values for the map f lambda will be obtained from the singular values of f by applying this change of coordinates in the range. So they will all be holomorphic functions. If this is v lambda naught, all the singular values will be holomorphic functions of lambda, and same for the critical values. And they will not be allowed to collide. It's really a holomorphic motion. I'm not going to define holomorphic motion for today. But what you have to keep in mind, the way I like to think about it, is that singular values keep their identity. You name them for your base point, and they will keep their type and their individuality throughout the whole parameter space. And in fact, you can prove that this is really a characterization of natural families. You are a natural family if and only if, so you have this double change of coordinates in the domain and in the range, if and only if, well, locally, if and only if all of your singular values and all of their preimages move holomorphically. So your rational side may be wondering, wait, what is the difference between taking the family of rational maps of degree D? And the answer is, when you have all rational maps of degree D, your critical values and your critical points are allowed to collide. While in this definition of natural families, they are not. And you could improve slightly the results, allowing some types of collisions, but this is not what we're going to talk about today. Another important thing is that these families of, these natural families, as far as I understand, were introduced by Remenko and Lubitsch for entire maps and by Epstein for meromorphic maps. And something very interesting, though we are not going to use it today, we will assume from the start that M is finite dimensional, but in fact, you can define maximal families of maps defined in this form, and they do form natural complex dimensional manifolds of finite dimension, and the dimension is exactly the number of singular values plus 2, which is given by a fine parameterization ambiguity in a way, I think. Okay, another important thing is that different types of families have been studied, for example, in the paper by Fajay and Keane, which kind of were looking for the same type of definition, though one in their paper is slightly different. And then other parameter slices, especially one dimension. So really, I think one of the features of this work is that you allow M to be finite dimensional, but one-dimensional slices have been studied before. For example, the exponential family has been studied a lot by Rempe and Schleicher, and then there are papers by Kotus and Chen, and so on. Okay, so what we have to keep in mind is natural family are families of meromorphic functions with finitely many singular values, and the singular values move holomorphically. Or, if you want to see it the other way around, they are maps with the same covering properties. You can forget about the definition till the very last slide. So now the question is, what are bifurcations? And really, bifurcation is one of these mythological words like love or justice or combinatorics that everybody uses, and everybody uses with quite a different meaning, actually. So the philosophy behind the idea of bifurcations is that you have an equation, which could be really anything you like. It could be a differential equation. It could be a variational problem. It could be a functional equation, an algebraic equation, you name it. But the point is, it depends on some parameter with an appropriate regularity. If your parameter is in R, it will depend continuously or differentiably. If your parameter is in a complex manifold, it will depend holomorphically. I mean, you name it. This is a very wide context. And in general, the solutions of your family of equations will depend nicely on your parameter, except at some points. At points where you stop having solutions, or the nice dependence on your parameter breaks, then we talk about bifurcations. And really, the precise definition of bifurcations is very much problem dependent. It depends on the setup that you take. So in dynamical systems, you think about bifurcations in terms of structural stability. So we define a map. You will take a family of maps, parameterized by some parameter for convenience. You don't need this parameterization. And we say that a map in this family is structurally stable if it is topologically conjugate all maps in a neighborhood. Or equivalently, there is a solution to this functional equation, the usual functional equation for the conjugacy, and you want your solution to be a homeomorphism, and to exist for every lambda in a neighborhood of lambda naught. So this, yes? Did I make something wrong? Not yet.
No. I mean, the definition cannot be wrong. But
well, I have to object. But anyway.
But if your map is, if your maps are not in the class S, would you not want your conjugacy also depend continuously, at least, on the parameter?
Yes, I think you want your conjugacy to depend continuously on the parameter, but I don't remember. So yeah. If you say so, I bet it's true.
So I think in the class S this will follow kind of automatically because you'll have a holomorphic motion and things. But
okay.
In general, I'm not sure. So.
It's possible. Okay. Like when you look at diffeomorphism, CK diffeos, I don't know. I would need to check. Katok Hasselblad has a whole paragraph on why this is the right notion and what kinds of maps are good and what kinds of maps are not.
It might also be that this only happens when you talk about J stability rather than structural stability. Anyway,
no J stability. You are not entitled to talk about J stability.
Okay,
the next slide. Okay.
All right, thank you.
Anyway, in general, in dynamical systems...
Can I say something?
Yes?
Because it's sort of unclear if you're talking about the class S or you're talking about general, because before you were saying
I am going to give
values.
results about class S.
Okay.
But I kind of want to set this in context, because there is a lot of confusion about bifurcations. So I kind of was trying to set this in context, more general context of dynamical.
Because also this natural family, there was no mention of class S.
No, so natural families you can define in general. Our theorems will be for class S.
But somehow there should be like something which are like at the boundary. If you have sequences of critical points that accumulate on another critical point, and the ratios are not sort of the same kind, then they would be topologically conjugate in that sense, but not quasi-conformally. So
I think so. This is unrelated to natural families for now.
okay.
Okay, and in natural families, the critical points are only accumulating at infinity. They're not accumulating on each other. For meromorphic maps, critical points are only accumulating at infinity. Maybe I misunderstood your question.
Yeah. So, but you were including also these asymptotic values. Can't they accumulate?
So, natural family is this, and you can do this also for. You can define this also for bounded set of singular, even if the singular values accumulate. The singular values are allowed to accumulate, indeed. But the critical points are not. And the concept of natural family is much wider than just class S, as far as I understand. And sorry if I created confusion. So a general problem in dynamical system is to study the structural stability and to show that structural stability is dense in appropriate spaces. And the complement of the set of structurally stable parameters is called the bifurcation locus. So this is in general in dynamical system, and now let us move back to complex dynamics. So in complex dynamics, what people usually study is not really structural stability, is J-stability. And the definition of J-stability is that a map is J-stable if its Julia set moves holomorphically in a neighborhood. And it's always implicitly assumed that this holomorphic motion respects the dynamics, so that J-stability really means topological conjugacy on the Julia set. And the reason, to my limited knowledge, of why people consider J-stability instead of structural stability is somehow because of centers. So if you think just about the center of the main cardioid, z squared plus 0, the fixed point is degree 2, while right nearby the fixed points are of local degree 1, and so somehow you're removing this kind of behaviors, which are clearly not topologically conjugate, but still have essentially the same dynamics on the Julia set, which is the set encoding the chaoticity of the map, and in a certain sense, debatable sense, the more interesting object to study. Now, there are two main features which makes bifurcations in complex dynamics very different from other types of bifurcations, again, in my view. And the first one is that, you remember, bifurcations come from this idea of studying this functional equation of finding a conjugacy, okay? And now we transform the concept of stability in terms of holomorphic motions of the Julia set. I'm not going to define a holomorphic motion, but for the 3 people in the audience who don't know, let me draw you a picture, okay? So what is a holomorphic motion? The holomorphic motion of a set, you should imagine the following. You have your manifold on the bottom, like usual, and you have the vertical fibers correspond to the complex plane. So what is a holomorphic motion? Is a family of injections of a set. So you fix your base point parameter, in this case 0. 0 is, well, lambda naught is more appropriate. And you take your favorite set. And what a holomorphic motion is, it means that for every other parameter, that each one of these points in this set moves injectively throughout the space. So in each one of these vertical fibers corresponding to C, you will see a deformated picture of your initial set. But this will be an injectively deformated picture. So really, in a sense, the set keeps its topological and even geometrical structure up to a certain extent. So, and one of the very powerful theorems, there are lots of very nice things about holomorphic motion, but something very nice is the so-called lambda lemma, which tells you that if you have a holomorphic motion of a set, so a set which moves in a nice way along the parameter, in each point keeping their identity, so really a family of injections, then you can extend it to the closure. And if you were respecting the dynamics, the extension will also respect the dynamics. So we all know that the Julia set is the closure of repelling periodic points. So what does this lambda lemma tell you? That if you want to move holomorphically the Julia set, all you have to do is moving holomorphically the periodic points in view of the lambda lemma. And so suddenly, we are looking at algebraic equation defining periodic points and look at bifurcations of periodic points instead of looking at the functional equation defining conjugacies. So this is the first main specialty of bifurcations in holomorphic dynamics, in my view. And the second special feature is that it's linked to activity of singular values. What do we mean? So what do we mean by activity of singular values? No, first let me tell you the big theorem, and then we talk about what activity means. It will stay a mystery again for this slide. So, but what I was telling you about this special feature in holomorphic dynamics is kind of put together with much more by this theorem by Magnier-Sullivan and Lubitsch for rational maps, and Deremenko and Lubitsch for entire functions with finitely many singular values. And it essentially states the following, that if you take a natural family of rational entire maps with finitely many singular values, then it is equivalent to say that you have J stability, so that the Julia set moves holomorphically in a neighborhood of a parameter, and to say that all singular values are not active or passive, if you prefer. And then you have many more equivalencies, but we're not going to really bother with them today. What is important is that the corollary is that J stability is dense in these families. And to prove density of the structural stability, even given this equivalence between holomorphic motions of the Julia set and passivity or non-activity of the singular values, you really need to use that you have finitely many singular values in your family. So it's really, the fact of having finitely many singular values seems to be really crucial to get density of J stability with this path. Now, what is an active singular value? This is a bit of a weird definition if you have never seen it before. So we say we take a natural family, and we take a singular value for f lambda. Now remember what we said in the beginning. Natural family means v lambda, so given you pick the singular values of one of your functions, and all the others, for all lambdas in the family, will be holomorphic motions of your initial singular value. So these v lambdas are really holomorphic motions of the other singular, of a specific finite set of singular values. And we say, and this is depending holomorphically in lambda, okay? This is active at some parameter if either your family of iterates is not normal in the neighborhood of lambda naught. And let me spend a second about this for people who have never seen this before. So v lambda is a singular value, depends holomorphically on lambda. Okay, lambda is in the parameter space. What do? You iterate, you look at its iterates, exactly like when you look at defining the Fatou and Julia set, but you do it for its own very special function, f lambda. This is a holomorphic family defined from a parameter neighborhood where lambda lives. This is holomorphic in lambda, okay? So this is a holomorphic family defined from your finite dimensional parameter space M to C. So normality makes perfect sense. You don't need to go into any fancy definition of normality. And to say that, that this family is normal is like saying that, similar to saying that you're in the Fatou set, so that all points in a neighborhood move together. So to say that this family of iterates, which is not really iterates, so that this family, depending on lambda, is normal, is kind of saying that all of your singular values in that neighborhood behave more or less the same. if it's not normal, it's kind of saying that you're in the equivalent set of the Julia set, and so that your singular values will do something different in the neighborhood. So far so good. This is only new for a few people in the audience, but now there is something that is probably new for most people. So you are active if either your family is not normally in a neighborhood of lambda naught, or it is not even well defined in a neighborhood of lambda naught. So do you remember in the very first slide, I told you, pay attention because some orbits are not well defined. Okay. Now I am looking at this family of functions depending on lambda. What happens if for some lambda naught, v lambda naught is mapped to infinity after a certain number of iterations? I cannot iterate forward. I cannot even look at normality of this family of functions because it's not even well defined. I cannot define f to the n plus 1. Okay? So this is another way in which singular values may be active and somehow breaking stability in a parameter neighborhood. And this is very important for us because we will see that this is linked to a new type of bifurcations that can only occur for meromorphic map. They don't occur for rational, they don't occur for entire. So let us go to our bifurcations of periodic points and look and see if something different can happen when you look at these meromorphic maps. We take our natural family, and now our equation will be the algebraic equation defining periodic points of some period k. We all know this. It's dependent on a parameter lambda because each f lambda will have its own periodic points of period k. We can look at the algebraic equation f lambda to the k of z is equal to z. These are the periodic, these are the periodic points of period dividing k. Yes, dividing. And we can look at its solution. So these are not the points of period exactly k, okay? These are all points which are fixed by f to the k. And we can look at a set of periodic points, and instead of looking at it for one single function, we look at it as the set of periodic points for the whole family. So really, when you look at a point, this is periodic for a specific function in the family. So you want to consider it as a couple lambda z, where lambda is the parameter, it tells you for which function you're periodic, and z is your point, it tells you which point is periodic. Okay? So the solutions are really the couples lambda z, such that f lambda to the k of z is equal to z. And where is this contained? This is contained in your manifold times, well, the c hat there is there for a reason, but I'm not going to talk about it. But let us look very quickly at this picture. So, well, what will happen for meromorphic maps, we said that because the Julia set is the closure of repelling periodic points, and thanks to the lambda lemma, we are reduced to studying bifurcations of periodic points. And there is really a new type of bifurcation that can appear for meromorphic map, is that some periodic points may go to infinity. But the point is, they don't go to infinity when you move towards the boundary of your parameter space. They go to infinity when you move towards a parameter which is really in your parameter space. So you can have a picture like this. I'm going to say more on this. But if you pick a function, f lambda naught, it has a certain number of periodic points of period k. In fact, there's infinitely many, but I clearly only drew a few of them. And if you are at a good parameter, locally, they will be all holomorphic functions of lambda, and this, they will all be locally holomorphic functions in lambda. But then you can have, I'm going to explain this better later, but you can have that some of these periodic points may merge, creating a parabolic cycle. This can also happen for rational maps and for entire maps. And you have something very new. This is some solution of your algebraic equation may be a point which converges to the boundary of the domain of definition. And we say that this periodic point is disappearing at infinity. One very simple example. I'm not giving the example now. Sorry. Well, anyway, the point will be we will have a new type of bifurcation, and the point will be to establish a relation between this new type of bifurcation and activity of singular values. Why? Because our goal will be to get some type of Magnéset-Sullivan theorem in which we link the bifurcations to activity of singular values, activity as defined in the previous slide. So either your family of iterations of the singular values are not normal, or they are not well defined. So what can we say about bifurcations of periodic point? We say that we have a bifurcation if there is no neighborhood in parameter space in which each solution of this equation is a holomorphic function of lambda. So for example, just to say, here, near this parameter, all of these solutions are nice holomorphic functions of lambda, or if you want, the projection is a nice covering map. When you get to a parabolic cycle, as a function of lambda, this would be, near this parameter, this would be a multivalued function, which we don't like for historical reasons, apparently, but we don't like it. And the projection will have a critical point. Really, look at the picture. This is a critical point for the projection map. When you look at this type of parameters, that we haven't yet proved that they exist, but they will exist, when you look at this type of parameters, near this parameter, you cannot define this solution as a holomorphic function of lambda, and look at it, this is exactly an asymptotic value for the projection map. Because what is, again, the definition of an asymptotic value? You have a curve moving to infinity, and the projection of this curve will move to a finite parameter in parameter space. Okay, so we have a bifurcation if there is no neighborhood of my parameter in which each solution is a holomorphic function of lambda, and there are many other ways of seeing it. I'm only going to look at this one, which is the one I just explained. You can think of a bifurcation parameter as a parameter which is a singular value for the projection, which brings you from the set of periodic points of period k, this variety of periodic points, to the parameter space. And this is the same picture that you have there, and you can prove it. And I didn't put ABF there because this is not the key point of the work. You can prove it. It's not difficult, that all the bifurcations are either cycle collisions, which are parabolic cycles, which are these bifurcations in which you have critical values for the projection, or cycles disappearing to infinity. Or, well, they could accumulate. We're not going to get into this. But really, you can phrase your bifurcations of periodic points in terms of singular values for this projection map, which is really what was already done in the paper by Eremenko and Lubitsch. Maybe with, well, it was clearly what they had in mind, I think. We can ask the authors later. But, OK. So, in fact, what is interesting is that different families allow for different bifurcations. A priori, there is no reason why this picture of points going to infinity could not appear for entire maps. But in fact, Eremenko and Lubitsch prove that you have transcendental entire function, and sorry, it's finite type, okay, finitely many singular value always. All bifurcation of periodic points are of parabolic types. And this is the main point that you need in order to prove Magnéset-Sullivan for entire functions. Again, sorry, there is a typo with finitely many singular values. This is not specified. Well, for rational maps, this is kind of easy, because you have finitely many periodic points of every period for every map, and if one of them moves to infinity, it's because your parameter is moving to infinity. Okay? But here, again, I know this is a bit weird, but the point of these cycles going to infinity is that you go to infinity, but your parameter is not in the boundary of your parameter space. It's really in the parameter space. So these are actual parameters. I will show you a picture later. Now, for meromorphic map, the opposite is true. So if you assume for minimal working conditions, the ones such that this type of parameters can exist, this type of bifurcation, these asymptotic bifurcations, are dense in the bifurcation locus. So completely different pictures. And the conditions you need is that you need to have active asymptotic values, and you need to have non-omitted poles. You need you need it to be possible to have the following picture, to have an asymptotic value which goes around a certain number of times, hits a pole, and is mapped to infinity. Once this is allowed, so you have active asymptotic values and non-omitted poles, then suddenly bifurcations of this asymptotic pipe become dense in parameter space. I think this is quite striking. And so the two main, let me try to explain you heuristically why you need meromorphic maps to get this type of bifurcation. So this is a theorem, okay? But let me just try to tell you what is going on when you have meromorphic maps that cannot happen for rational maps and for entire maps. And this will be a bit more precise later. So what happens now? Imagine to crush all of your dynamical planes, so here we have a picture in the product space, right? My parameter space and my dynamical space, and each map has its own personal dynamical plane. Now we crush them all together. So C is not a dynamical plane for anyone anymore. This is like all of them put together. And here we have some periodic point Z of lambda, which is the one which is converging to infinity. Sorry, I'm putting infinity here. I know it's not appropriate. We usually don't see infinity, but it's here. And what is this Z lambda? Each point here is fixed under F lambda, okay? So this is not a curve of fixed point. This is a curve in C, which now has no real dynamical meaning, and each single point in this curve is fixed by F lambda to some power. For example, 3. Minimal working example. Now, if you have an entire map, you could go back from infinity to an asymptotic value. So this is as lambda converges to some lambda A. So we are supposing they converge to infinity. So they converge to infinity as my parameter converges to an asymptotic value for the projection map, okay? So for lambda, for the asymptotic value of the projection, this fixed point will become infinity. And somehow, in the end, you will get what is called the virtual cycle. I know I'm not being very precise here, but what can you see it happens? So you can go back to the finite part of the plane by using these unbounded preimages of neighborhoods of asymptotic values. But then, if you have this, you can only do if you have asymptotic values, right? Rational maps, no way to go back from infinity to the finite part of the plane. But then, in order to close a cycle, you need a way to go back from the finite part of the plane to infinity. So you need your image to be mapped to a pole. And then the neighborhood of a pole goes back to a neighborhood of infinity under the limiting function f lambda a. So if you had an entire map, you would have no poles. So the only way to get this kind of limiting behavior would be if all points in your cycle converge to infinity. And Eremenko and Lubitsch, what they do exactly is to show that this cannot happen. You cannot have that all of your periodic cycle converges to infinity together. So really, in order to create this kind of limiting behavior, which is a kind of limiting behavior that is possible, as I told you, these type of bifurcations are dense in many spaces of meromorphic maps, you really need both asymptotic values, transcendental functions, and poles, meromorphic. So what are the two? Yes.
Could you just say again, so what is your exact assumption on your functions in this theorem?
You need non-omitted poles and active asymptotic values.
Okay, so active critical points.
You need asymptotic values. I think the assumption we have is you need at least one active asymptotic value and at least one non-omitted pole. You need this behavior to be possible. Okay, so you need your pole to be non-omitted because it must be the image of your asymptotic value. And you need the asymptotic value to not be mapped persistently to infinity.
If you work in the maximal family
Yes.
with the given dimension, then is the activity automatic?
Well, if you have the sign map, which has no asymptotic values,
Well, forget entire. I mean, in your context.
if you have a
I mean,
meromorphic map with no
I agree.
asymptotic
Infinity's
values,
not active in that
or if
case.
so if I think what you're saying is, if you take a maximal family, and you do have asymptotic values, they will be active in some slice.
As
And in
long as
this
it's not
slice,
entire.
you will have density, but I think you will have density in the slice. You could have some slices on which your asymptotic value is not active, right?
But somehow only on a slice? Doesn't that have... Maybe I need to look at this after. Well, we can talk about it afterwards.
No. I think it's a good point. Well, you need to be... The reason why it's ingrained, it's not stated precisely, is because it's a bit delicate. But essentially, whenever they're allowed to happen, so you have asymptotic values, which are not persistently doing something, and you have poles, then this new type of bifurcation is really dense. So not only they exist, they are everywhere.
But I mean, you wouldn't have persistence except in the entire case, right? If you have a maximal family.
If you have a maximal family, it would not be persistent on the whole
Yeah.
thing. Yeah. Yes, exactly. But you still need the asymptotic values to be there, because you could have families with only critical values. Well, anyway, the two main points of proving Magnet-Sullivan for meromorphic maps with finitely many singular values in natural families is really to link these new types of bifurcations, we call it the activity theorem, to these new type of bifurcations of periodic points to active and to active asymptotic values, or active critical point is a technical condition I don't want to get into it, but in general you are able to say that this, well, in general, if there are no nearby active critical points, this asymptotic value, which is kind of naturally linked to our points going to infinity by this construction, so the main point is showing that this asymptotic value, if there are no active critical points around, is active. And it's kind of a modification, if you want, of the proof by Remenko-Ljovic, but with a lot of little more technical difficulties and a few new things to look at. And then the other thing that you really need in order to prove the Magnet-Sullivan is to say that if you have one of these new types of bifurcations, you want to treat this new type of bifurcation, these virtual cycles, as they are called even by Linda Keane and Nura Fageya, you want to link these new types of bifurcation, you want to think of them as being virtual centers. So you want to think of them as being the limit of attracting cycles whose multiplier tends to 0. Okay, so these are another very important, these are the two main parts to prove Magnet-Sullivan. Let me also point out that you have a lot of, like the proof of density of Misurevich parameters in the bifurcation locus. You have a series of proofs which you use Montel for. You take your definition of activity, this is for the experts, okay? You take your definition of activity for the singular values, and there are several proofs using normality. If you're normal, you cannot admit more than 2 values, so you must hit whatever thing you want to hit. So these type of arguments all needs to be changed and replaced, because now your activity may be due to non-normality, but it may also be due to failure of your functions, even be well-defined. So let me point that these are all arguments that work through, but you need to do them in a different way. So the accessibility theorem is here in order to show you this picture. And this is the bifurcation locus for this family, tangent square of z. And the pointer is here. And look, here you have the usual copy of the Mandelbrot set. So parameters here are nice centers. And these centers of the butterflies are the virtual centers. These drop-shaped components are hyperbolic components. And this pointer is gigantic. On each one of these internal rays, you converge to these centers, which are virtual centers. So parameters for which some asymptotic value is mapped to infinity under a certain number of iterations, and which will exhibit this type of behavior of your asymptotic value going to a pole and going to infinity. And the parameters on curves converging to your virtual center, so for example, parameters in the center of the drops, will have attracting cycles which go all the way, for which one point will go all the way to infinity, one point will converge to asymptotic value, one point will converge to a pole. Well, there could be finitely many steps in here depending on the period of the cycle. And this is kind of what I wanted to say today. We get the theorem of Magnus-Sullivan. So thanks to this activity theorem, we are able to conclude that bifurcations of periodic points only occur if you have active singular values. In the parabolic type of bifurcation, you proceed exactly like you do for rational maps. And in the new asymptotic kind of bifurcation, you proceed to this linking these new asymptotic types of bifurcation to activity of asymptotic values. And as corollary, again, using in a crucial way that you have finitely many singular values, you get density of J stability. So this is really like Magnus-Sullivan theorem, well, Magnus-Sullivan U, which would be more accurate, for meromorphic maps. And now the natural question. Of course, you can prove many more equivalencies, okay? The experts know that there are a whole zoo of equivalencies that you can prove. Anyway, the question is, could you do more? And the answer is not much, okay? So how could you do more? You may want to allow for infinitely many singular values. And there is an example which is in many senses optimal by Epstein and Rempe. This is not written up, and since both authors are here, we could put a little bit of pressure on them to publish this. But there are very nice slides by Epstein, which are very convincing, and if you look through them, filling in the details, you would be able to reproduce the proof. So I really think this is not published, but this is true. They have an example in which you have a map, and the family you consider is simply the family of translate, f plus c, where c is a parameter on the disk. And you can show that the bifurcation locus of this family inside the disk has non-empty interior. But somehow, the set of singular values for this map F are dense. So if you consider them, the set of singular values to be a closed set, they really contain an open neighborhood, okay? Remember that for transcendental maps, singular values are in general not isolated if they're infinitely many. They can accumulate. You can construct entire functions for which every value in the plane is singular. So really, in the example by Epstein and Rempe, you could argue that the bifurcation locus has empty interior because there is an open set of singular values which is bifurcating. But you can do a similar type of things, well, with different techniques, in which you can construct a function. This is a work in progress with Astorg and Fageia. You can actually construct a map F, which has infinitely many singular values, and your family will have a bifurcation locus which is non-empty interior, but all your bifurcating singular values are isolated. For the moment, we cannot really control how are the other singular values doing, but the ones that we know are bifurcating, the ones that give you the bifurcation locus in non-empty interior are isolated. So this is, I think, is kind of interesting. So there doesn't seem to be very much space to prove a general theorem of empty interior of the bifurcation locus if you have infinitely many singular values. Of course, you may be able to do something in very specific families. And the other thing which is kind of interesting is that our results are, in a sense, local. So they apply to the class of finite type maps which has been introduced by Epstein, which are maps for which a domain definition is no longer the whole complex plane, but they are like potentially smaller domains, possibly not connected. And we do need some technical assumption here, but somehow this type of techniques, studying this new type of bifurcation, kind of, in a certain sense, closes the problem for one-dimensional maps with finitely many singular values. And it's time to wish Carsten a happy birthday. And thank you for listening to this talk.